I have watched a number of videos on YouTube featuring factorials, which has inspired me to do my own, in which I will try to go deeper in depth than I have seen in some of these other explanations. So let's begin. We're going to break this explanation up into 7 parts. The impetus for why we would be interested in factorials, looking at some strange factorials like 0 factorial and negative factorials. We will then look at the Pascal Triangle as bringing a lot of mathematical topics together. We will then go into fractional and complex factorials, and then look at the plotting of these factorials. We will then go into binomial expansion, where this is the real heart of where the factorials get used. We will then develop some factorial formula, and then we will apply what we've learned from that. So let's begin. The definition of a factorial is 3 factorial, where the exclamation mark is the symbol for that, is written as that number times every number below it until we get to 1. So 3 factorial would be 6. 4 factorial is written 4 times every number below it, and that would give us 4 times 3 times 2, 1 times 1, but 3 times 2 times 1 is 3 factorial. So from this we're deducing that the factorial can be written as that number times the factorial below it. Okay, now how would we use factorials? Well, we use factorials by the way we can arrange things. So if we had 3 boxes and we had 3 different objects to put in those boxes, we could have 6 different arrangements. We have a choice of 3 for the first box, 2 for the second box since 1 has already been used, and 1 for the last box. And that would give us 3 times 2 times 1, which is 6. Now, suppose some of these objects that we're arranging are alike. We wouldn't be able to tell the difference between the 2 that are alike, so that particular combination would have to be eliminated. So the number of ways that we can arrange things is, say, q, if we had q of them. And so there would, if we had, say, for example, 3 that were alike, then there's 6 different ways those 3s could be arranged. And so we could eliminate 5 of those to get a unique pattern. This can be illustrated by the following. We have 2 A's and 3 B's. The way we could arrange all those, if they were different, would be 120 ways. Since 2 A's are alike, we'd have to divide by 2 factorial. And since 3 B's are alike, we'd have to divide by another 3 factorial. And so we do the arithmetic, and we find that we get 10 different arrangements. Now, one of the reasons for knowing this ahead of time is because it's hard to figure out what those arrangements are. So I just did it with the A's to show how we could find it, and you can throw the B's in. First, we had the A's together, separated by 2, separated by 3, and separated by 4. Then I moved the A over 1, and again, 1, 2, 4 arrangements. And then I moved the A's over 1 more. And then I tried to separate the A's. And when I went through all of those arrangements, I found that there were 10 arrangements. So I felt comfortable that I found all 10 arrangements. Another example of the way we could use this is if you were in a dance studio and you had, say, 10 people, how many different lists could you make? Well, the way to solve this problem is by taking the simplest case, which would be 4 people. With 4 people, if we had A picks a partner, then there are 2 people left. And of those 2 people, they have no choice, they're going to be partners. Well, A can pick any one of the 3 remaining people. That's what this says. Pick any one of the 3 remaining people. But then once that's done, the next person can't pick themselves, nor the 2 that you've picked. So we go down to 3 less than n, and so on down the line. We then sort of test this out with 6 people, where we start off with A picking any one of the 5 remaining people. And then once he's done that, he's got 4 left. And we know there are 3 ways that we can arrange those 4 people. So we have 3 times 5 comes out to 15. Now, there are some things that we can do with factorials that become interesting. First is, what would 0 factorial be? Our first guess would be that it would be 0 or undetermined. But if we go back to our definition of factorials and we divide both sides by n factorial n minus 1 factorial, we get a reciprocal formula. And now let us make use of the fact that 1 factorial is equal to 1. Okay, if we substitute n equal 2 in this formula, we get 1 over 1 minus 1 is 2 over 2 factorial. Well, 2 factorial is 2, times 1 is 1, divided into 2 gives us 1. Now let's try n equal to 1. 1 over 0 factorial is equal to 1 divided by 1 factorial. That's equal to 1. So 1 over 0 factorial is 1. Now you may wonder why we're looking at the inverse, and I will show you that in a minute. But we could also see that 0 factorial would be 1 because 1 over 1 is 1. But now let's try n equals 0 in that formula, and we get 1 over negative 1 factorial is equal to 0 over 0 factorial. Well, we know 0 factorial is 1, so this is 0. So 1 over a negative factorial is 0. And you can now see why I wanted to look at the negative, because if I had done it the other way, I would have had division by 0. And I keep doing this with different numbers, negative 1, negative 2, and I begin to see a pattern. And that pattern can be represented by this formula. 1 over 1 negative factorial is equal to minus 1 raised to the m minus 1 power. We can see they alternated when we were looking at them before, times m minus 1 factorial divided by minus 1 factorial. Okay, so if we ignore the fact that minus 1 factorial is 0, we have a formula here that we can use later on to determine some interactions with negative factorials. Now we move on to the Pascal triangle. For most of us, the only part of the Pascal triangle that we're familiar with is this lower right-hand corner. We obtain numbers by adding the number above that number and the number to the left. So 3 plus 3 is 6. But if we look at this top corner here and make note of the fact that these are all 1s, so we'd assume they're all 1s up here, then in order to get the 0, we'd have to add negative 1 to this. In order to get this 0, we'd have to add 1 to that. Okay, and likewise, we could keep going up each of the rows. We went over here, we could see adding 0 to 1 would give us 1. So that has to be 0. Adding 0 to 1 would give us 1. Fine. Even up here, we can see the same thing, except there's 1 here, which is an anomaly. We'll discuss that in a minute when we continue with the rest. So we can see why all of these over here would be 0. Now, we would see that we'd have to have a minus 1, 1 pattern going all the way through, and this works here to give us all these zeros. But if we go over to this one over here, 1 plus 1 is not equal to 1. So that is a little bit bothersome. And the rest we could also, once we have this, minus 3 plus minus 2 is 1. Minus 2 plus 1 is minus 1. And so we begin to see some patterns in here. We see this pattern is repeated in the vertical direction on the upper left-hand side. And this vertical pattern is repeated in the horizontal direction on this side. And in fact, if we look at this carefully, we see this is the same thing. We see these 2 zeros being picked up over there. And over here with this, we see 1 0 being picked up. Okay, and the signs are all okay. Now, what do we do about this anomaly? Everything else works fine except for here. Well, let's replace them by negative factorials or by factorials. And so we could see that these factorials will come out the numbers in here. And we'll note that when we get past this first column, we have a 0, and we'll notice that we have a negative factorial, just following the patterns. So that we explain why we get that triangle of zeros. When we go up here, we get two negative factorials. And you see the -1 and the -1? But if we don't think about that as 0, and think of a limiting process, then something divided by itself is 1. Over here, the -2 factorial will again have, if we looked at our previous place, the -1s will continue. So when we have those two negative factorials and we reduce them to a -1 factorial, we see that they reduce and we get these numbers here. So we're basically getting a 0 by 0, which in this case, we're assuming is 1. And if we go over on the other side, you'll notice here we had two negative numbers in here, that we will also begin to see that these will generate the same numbers that we have over there. But if we try to prove that when you add a number to itself as below, if we do this in terms of a factorial formula, where we're taking the row above and to the left and the row above and adding them together, we will get the row below it. So that is a general case formula. So now what we do is we pick the case where we have n is -1 and m is -1. And when we do that, we get our -1 factorial over our -1 factorial, which we assume is 1. So basically, there's an anomaly in here, and we get 0 divided by 0. In this case, we're going to assume that 0 divided by 0 is 1. So we've now explained that with the mathematics. Now, there's another way of defining factorials, and what happens if the numbers are decimal numbers or complex numbers? Well, Gauss had figured out a formula such that if we integrated from 0 to infinity, x to the nth power, e to the minus x dx, and we integrated that by parts, that would be equal to n times n minus a function of n minus 1. Looks like factorials in that case. So if we took the case of putting n as 1 or n as 0, which is even easier, we would then be able to find out what the different factorials were. Okay, and we showed a case here. We put n equals 0. We did our integration. We got e to the 0, which minus 0, which is equal to 1. So once we establish that, we now know from this formula that we can just use it recursively to get the rest of the factorials. Turns out an interesting phenomena to take advantage of some of functions in calculus, that you can show that you will get the square root of pi divided by 2. Now, there may be other similar anomalies around, but the fact that it was for 1/2 sort of makes us think about it. But in general, we don't necessarily think that they have to come out as we don't have to think about them coming out as some other combination of rational numbers. And in this formula, for n, we could put I. So we'd have an I here, and we could then use Euler's formula, which would expand it out to a real part and an imaginary part. And if we did numerical analysis, we could find out that the real part was approximately 1/2, and the imaginary part was approximately -0.15. Now what I'd like to do is plot in the real space 1 over x squared. And the reason for that is that we know at negative numbers it will go off to infinity. So this is the function plotted as an inverse, and we can see on the positive side it continually goes down, pretty much like an negative exponential function. And as we go to the other side, we can see that it starts decreasing, goes through 0, comes back, and these oscillations get bigger and bigger. We see a sinusoidal pattern in there. If we did not take the inverse, here is the factorial as we would know it for integers, and this is what happens with fractions. As we get near to -1, we know it's going to go off to infinity. But then we saw those alternating signs, which says then it's going to pick up at -infinity, come back again. And so we can see these infinite loops that are deriving in there. And they're getting closer and closer to the origin. Okay, so drawing this picture gives us sort of a view and makes us feel maybe a little bit more comfortable with negative fractions, negative factorials, particularly in this inverse form. Okay, now we're going to look at the binomial expansion. And we will see in a few minutes why that binomial expansion is important. So we multiply a plus b using the distributive property, multiplying a times the first row and multiplying b times the second row. Adding these together, we get this. And if we assume the coefficients that are not shown are 1, we have 1, 2, and 1. We do this again, and we get coefficients of 1, 3, 3, and 1. So these coefficients are following the Pascal triangle. Well, we could replace those by the factorial coefficients, and we see an interesting pattern. The top numbers are 3, matching the exponent here. The bottom numbers add up to 3, but start off with 3, 2, 1, and 0. And the other number increases. You'll also notice we threw a B0 in there to maintain that pattern of exponents and factorials, because any number raised to the 0th power is 1. And similarly, we had an A0. Now, once we have this formula, we could put 1 in for A and B. And if we did that, we get this particular factorial formula. We could also put -1 in B, and we get the same thing with alternating signs. And because we know this is equal to 0, this must be equal to that. And we'll notice here, we're skipping terms. And I tried to write out a formula for both the positive result and the negative result to describe what the answer would come out to be. So if we took, in this case, 1 over n is 4, 1 over 4 factorial, 1 over 2 factorial, and 0. So we can see we're skipping 2, and we stop when we get to 0. If we started with the 3, we get 3, we go down to 1, and we get a negative number, so we stop here. And we find out, interestingly, that these now are equal to one another, and that when we add them up, they are going to add up to 1 plus 1 cubed, or fourth, since we're raising the 4th power. But since we're taking alternative terms, it's half of that, since we showed the positive and negatives are equal. And you'll notice the 4 factorial is missing the top. We just divided by 4 factorial. So it gives us an interesting formula. Now we take and apply this. We know that we can write the sine and cosines as infinite power series, which are derived from the exponential function by putting in I x or iy for the variable that e is raised to. And this gives us a imaginary part and a real part. Okay, and so now we're going to multiply these two trigonometric functions together. And we multiply them, you do the binomial expansion, except this time we're multiplying fractions, and we're multiplying negative numbers, so signs are inverting. And so when we multiply this times each number in that gives us the first row. When we multiply by the negative number, it gives us the second row with signs alternating. And we keep doing that. And then we begin to notice a pattern. And we also notice that we had shifted everything over. We shifted it over because we wanted to expose that pattern. And we drew the line at an angle rather than straight because we can see that this is a growing, the columns are getting bigger and bigger. And so now, if we take a look at all of the coefficients of x cubed, we have this term in here and these terms in here. And we might recognize this. Oh, that has something to do, well, it starts off with a number and a 0. So we figure that has something to do with cubes. The same with here. That would be do with 5s. And if we look back, we begin to see why we needed this formula. And so now, for the coefficients of x cubed, that's going to be reduced to 2 to the cube divided by 2 times 2 factorial. And 5 is going to be the same thing. If we then we see the cubes, we can make this 2x cubed. So now we're just left with the 3 factorial. I made a mistake here. And we can replace the x with 2x to the 5th divided by 5 factorial. Didn't make a mistake there. And if we factor out the 2 from the bottom 1/2, this gives us the following series, which we look up here, it's the same as the sign, except we have 2x instead of x. So this must be equal to 1/2 times the sine of 2x. And for those who are familiar with trigonometric formulas, the sine of 2x is equal to 2 times the sine of x times the cosine of x. So what we've done is we've taken the subject which doesn't get too much attention, and when it does, rather sparse, and we showed how we could solve a problem which would have been very difficult. It took me years to figure out how to do this with the power series because I always felt that I should get the same result when I multiplied the power series as I did when I multiplied the functions. And thanks to the factorials, I was able to do that. So hopefully you've enjoyed this little session, and we'll take the time to play with it so that you can get a more appreciation of the factorials and maybe find some problems that you can discover, that I discovered for myself. Talk to you later, guys. Bye.